Let's talk about the alternating series test. Now, I want to remind you that one of the conditions of the integral test was that each of the terms an had to be positive. Okay, so what I want to do is I want to look at something called an alternating series, and an alternating series is going to have the following form. It's either going to look like this with an infinite sum as n goes from 1 to infinity with a negative 1 to the n times b to the n, b sub n, or it's going to look like this. The infinite sum as n goes from 1 to infinity, negative 1 to the n plus 1 times b to the n. Now, what's the difference between these two? The first series on the left, this one has that the odd terms are negative. While the second series on the right, this one has that the even terms are negative. Okay, and the signs of each of these guys are going to continue to alternate. So it'll be like plus, minus, plus, minus, plus, minus, and it either alternates like that, or it starts off with, you know, negative plus, negative positive, like that. So it really depends on which of these two situations you're in. The alternating series test is going to test the convergence of alternating series, such as what we've described up above there. So if the alternating series is of the following form, either the summation as n goes from 1 to infinity of negative 1 to the n bn, or the situation we have this infinite sum, negative 1 to infinity, negative 1 to the n plus 1 times bn, where this bn is always greater than 0, so it's always a positive number. I think I forgot to mention that earlier. The sign is determined by the alternating piece out in front, and this bn is always positive here. When you have alternating series of this form, there's two conditions that we need to check. Okay, so the first condition is when we take the limit as n goes to infinity of those bn, those positive numbers, that limit needs to go to 0. And the second condition we have is that we need that those positive numbers, bn, those need to be decreasing. So those are decreasing. Okay, so when you have these two conditions, these are conditions. When you have those two conditions are satisfied, then the series is convergent. That's the conclusion. All right. Now I want to make a quick parenthetical comment here. There's two ways to show that a function is decreasing that I've taught you. Two ways to show. The first way is algebraically, and the second way is with a derivative. Okay. So we needed to show that something was decreasing in the past in order to use the integral test, right? So we've seen this idea before. Let's take a look at example 1. And this example 1 is classic. So maybe I'll mention that this is a classic example. Okay. So it's one that we should definitely want to keep in mind. So when I look at this series in example 1, we can see that we have an alternating piece. In this case, it's a negative 1 to the n minus 1. This has the same effect as negative 1 to the n plus 1. So the order of the signs will be the same in either case. So if I just change the way this series looks a little bit, I can rewrite this as the summation as n goes from 1 to infinity, negative 1 to the n minus 1 times 1 over n. And this piece right here, this is basically the same as negative 1 to the n plus 1. In other words, negative 1 to the n minus 1 and negative 1 to the n plus 1 will both have the even terms being negative. All right? So let's run our alternating series test. The first thing we're going to do is we're going to calculate a limit of the bn's. So if you take the limit as n goes to infinity of bn, that's really the same thing as saying the limit as n goes to infinity of 1 over n. And we can clearly see that this is going to go to 0 because the top here is a constant and the bottom is getting bigger and bigger and bigger and bigger and bigger. So it's like if you share one piece of pizza with, 2 friends, 3 friends, 20 friends, an infinite number of friends, you're going to have very little pizza left over for yourself. All right. Let's check the second condition. The second condition is we need to show it's decreasing. Show it's decreasing. And as I said earlier, there's a couple ways that we can do that. So let's say the algebraic method, we want to take a look at an plus 1 and see, is that going to be less than an? So let's check. So what does an plus 1 look like? An plus 1 looks like 1 over n plus 1. Is that less than 1 over n? And what we could do is we can multiply both sides by n. If you multiply both sides by n and then both sides by n plus 1, we realize that's the same thing as saying, is n less than n plus 1? Well, this is obviously true, right? This is n plus 1 is obviously bigger than n. So this is obviously true. I would even say, just looking at this first fraction, 1 over n plus 1 is obviously less than 1 over n because the denominator n plus 1 is bigger than the denominator n over here. So dividing by a bigger number results in a smaller fraction. So I could have stopped over here, but I did this weird like cross multiplication thing to make it super obvious. Okay. The other method that I had mentioned to you was with a derivative. So you don't have to show both ways. You could just use one way. I would use the way that's easier for you. Algebraic method works sometimes. Sometimes that's easier. Derivative method is easier other times. So why don't we let f of x be equal to 1 over x? Then an is going to be the same thing as f of n. Okay, so it agrees, our function agrees with our series on all the positive integers. So now let me calculate what f prime is going to be, right? So f of x is the same thing as x to the negative 1, and that tells you that f prime of x is equal to negative x to the negative 2. And what can we say about the sign of this derivative? This derivative is always less than 0 because you have this negative sign in front of your derivative. A negative derivative f prime means your function is decreasing. Okay? So what we've done is we've used two methods to show that both number 1 and number 2 are true. So let's say, therefore, by the alternating series test, the series converges. And I'm just going to highlight that because that is our answer. I think whenever you use an alternating series test or a ratio test or a root test or a comparison test or an integral test, you should always state which test you're using, just like we've done here. All right, everyone. We'll look at more examples in class. Take care.